Hello, everyone. Good afternoon. Welcome back. Nice to see you all. I hope you had a great break. I sure did. It was nice to get a little time off, get caught up on things, and also took a little trip with my family for a couple of days and got into mountain biking. So that was really fun. Let's see. We are in the home stretch now, right? You made it over the hardest part. And the rest won't be easy necessarily, but it won't be as hard as what we just did. So congratulations to you. The exam went well. Thank you for your hard work. And now we're going to continue into the topic of entropy, which is a topic that helps us explain why things happen, right? So in previous chapters, for example, on the chapter on equilibrium, we learned about chemical reactions and the equilibrium constant. We learned that some equilibrium constants were bigger than others, right? Which means that some reactions go further to the right than others. But we didn't learn why. We still haven't really broached that question. Why are some equilibrium constants bigger than others? Well, that's kind of the topic of this chapter. The topic of this chapter is free energy and thermodynamics, and what we're interested in is spontaneous processes and why do they happen? Why do some reactions go spontaneously towards products while others don't? That's the big question, and that's the one we're going to hope to answer and begin to understand. Okay? Before we get started, do you guys have any questions about anything?
The last exam is 1 week before the finals, right?
The last exam is, let me look at my schedule here real quick. The last exam is on Thursday, April 29th. And the final is on Monday, May 3rd.
And the final includes everything, or
Correct.
Like
The final is cumulative over the entire semester.
an equal proportion of all the topics.
Pardon me?
An equal proportion of all the topics.
Correct. Right. It'll cover everything covered on exams 1, 2, and 3.
Okay, thank you.
Yep. Yep. Thanks. Any other questions? Okay, let's go ahead and get started. Yeah, it is a cumulative final from the beginning of the semester to the end. It's not cumulative over the entire year, though. If we were live, it'd be cumulative over the entire year, but I decided to just make it cumulative over the semester simply because of the current situation. But if we go back live next year, it'll be cumulative over the entire year again. So it's you know what? It's just the way we learn. We learn by relearning. Interestingly, the first time you learn something, you kind of learn it. The second time you learn it a lot better. And the third time you learn it, it really starts to sink in and it stays with you. So that's why I do like cumulative finals. And again, I don't want to overburden you this semester because it's been a tough semester and a tough year, but it will be cumulative over 1 semester instead of 2. So that's the kind of COVID bonus, I guess. Not that we really want to have a bonus for that, but okay, good. Let's see. Oh, so someone's asking if it's cumulative over 155 and 156. The answer is no. It's just cumulative over 156. So it's just cumulative over this semester, the final. All right. Very good. All right. Let's get going here. Free energy and thermodynamics. The key thing to remember about all of this is this pervasive tendency of energy to spread out. So thermodynamics is the study of energy and how it interacts with matter, right? And it has the first law we learned last semester, if you remember. Does anybody remember what the first law of thermodynamics was?
Energy can't be created or destroyed.
Correct. Energy is conserved, right? So we know that in all chemical processes, energy is neither created nor destroyed. There is an exception to that. It is nuclear energy. In nuclear processes, you can create energy out of mass and mass out of energy. So really a more complicated form of the first law is mass energy can't be created or destroyed. But for our purposes, we can just think about it as energy is not created or destroyed. Now, the second law of thermodynamics is the one that governs the direction of all spontaneous processes. You may have heard in your physics class that objects tend towards lower potential energy, right? And that going towards lower potential energy determines the direction of change. But that's actually not really true. It's true for a lot of things, and it's true for mechanical systems, right? Like if you drop a ball, it's going to go towards lower potential energy. But there are some chemical processes that actually go towards higher potential energy, right? Like think of an endothermic reaction, right? Have you seen those chemical cold packs that you break a barrier and the substances mix? And what happens? It gets cold. Why? Because the particles, the atoms and molecules in there are absorbing energy and they're going towards higher potential energy. So if you're icing an injury, it takes heat away and cools it down, right? But the system itself is going towards high potential energy. So in chemistry, there are systems that will go towards high potential energy. So going towards lower potential energy does not determine the direction of change. What determines the direction of change universally for all chemical and physical systems is energy dispersion, all right? In all spontaneous processes, energy spreads out. And just think about it from your own experience, right? If you have a hot cup of coffee, right? What happens to the concentrated energy in that hot cup of coffee?
It disperses into the room.
Yeah, it spreads out into the room, right? The first law of thermodynamics, energy is conserved, would allow energy to go in either direction. So in other words, according to if we just had the first law of thermodynamics, there would be no reason why your coffee couldn't spontaneously get hotter while the room got colder, right? Energy can be conserved that way, but that's not the way our universe goes, okay? Our universe always goes in the other direction, towards a dispersion or spreading out of energy, right? So it turns out that that is the criteria for all spontaneity. So for a chemical reaction, if we want to know, well, why do some reactions have big equilibrium constants and other ones have small ones? The ones that have big equilibrium constants have big equilibrium constants because as they occur, they disperse energy. Energy becomes more spread out as the reaction occurs, okay? Those kinds of reactions have big equilibrium constants. Reactions where that doesn't happen have very small equilibrium constants, all right? So that's what determines it. In this chapter, we want to dig into the details of that so we can try to really understand it, all right? But at the end of the day, remember, energy spreads out. That's the key takeaway message. The overview of this chapter is just 3 words: energy spreads out, okay? And you see that all over the place right here. There's a computer monitor, it's hot. It spread, that energy doesn't concentrate in the computer monitor, it spreads out to the room. The hot lamp spreads out. Hot cup of coffee cools down as the energy spreads out. Okay, so since we're interested in spontaneous processes, let's start by trying to figure out what we mean by spontaneous, okay? So we know that if you have, a nice new car, right, over time, spontaneously it'll go in this direction, right? The iron will rust. So iron rusting is an example of a spontaneous process. Iron spontaneously rusts. Spontaneous process is one that occurs without any outside intervention. All right. And one example is iron rusting. Not all spontaneous processes happen quickly. So for example, it is spontaneous for the carbon in diamond to turn into graphite, right? but your diamond rings will last your entire lifetime and the lifetime of many more people, in fact, right? Because this process is very slow. The point of this is to not confuse spontaneity, which is how far a reaction goes, right? That is what thermodynamics addresses, right? That is what we're talking about in this chapter. But we don't want to confuse that with how fast a reaction goes. That's the study of kinetics, which we studied in a previous chapter, okay? And those are not necessarily related to one another. In other words, a reaction can go pretty far, it can be pretty spontaneous, but it could be very slow, which means it takes a long time to happen, right? Or a reaction could be pretty non-spontaneous, but pretty fast. So we don't want to confuse those. When it comes to spontaneity, what's important is the states of the reactants and products on this axis, which here is energy, but in reality, it's really free energy, which we'll talk about a little bit. We'll talk about quite a bit later on in this chapter. And kinetics has to do with the intermediates and how high in energy this intermediate state is, right? This transition state. So thermodynamics is related to the height of this and that. Kinetics is related to the height of that, the activation barrier, okay? So we don't want to confuse those two. We don't want to assume that just because a reaction is spontaneous means it'll get there quickly, okay? It may be spontaneous and be really slow. All right, I see a couple of questions real quick. Let me answer those. Taylor.
As far as the outside forces for the spontaneous process, for the rusting, if there's no oxygen, so it won't rust, is that how do I say this? Like, is that an outside force that there's oxygen there?
No. The idea is if you have iron and oxygen together, right? If you don't put any energy in or you don't do anything, will the reaction happen? So the reactant's got to be present. So spontaneity has to do with if these reactants are present, does the reaction spontaneously occur?
Okay. So like ice melting.
Yeah, exactly. Yeah.
Okay. Yeah. Thank you.
Yeah. Okay. So what we want is, again, in physics, we have this idea of mechanical potential energy. And we know that things, if we plot things in terms of mechanical potential energy, if mechanical potential energy goes up, we know that things go towards lower potential energy, right? That's the direction of spontaneous change. Wouldn't it be nice if we had something like that for chemistry, right? Something which actually it's called chemical potential, and we'll see later on, it's really called free energy, that determines the direction of spontaneous change. And again, in physics and in mechanical systems, all that matters is potential energy. In chemistry, what really matters is entropy. Now, it turns out they're both really related to the same thing, because if you think about this mechanical potential energy thing, right? Again, just like the coffee cup that was hot and had concentrated energy in it and it spread out over the room, right? In physics, this raised weight has concentrated energy in it as well, right? Concentrated potential energy, right? So what's the direction of spontaneous change? It falls to the ground. When it falls to the ground, what happens to the energy that it had?
It loses it and disperses.
Exactly. The energy disperses. Okay. So ultimately, chemistry and physics really follow the same law. The second law of thermodynamics is what determines spontaneity. And the thing about high potential energy systems is that they have concentrated potential energy. And so they tend to go towards lower potential energy to spread that energy out. All right. So ultimately, it's energy dispersion, right, that determines the direction of all spontaneous change, not just in chemistry, but in physics as well. All right. But again, we're looking for this kind of chemical potential, this nice way to be able to determine, this is at a higher something than this, so therefore it'll go in that direction. Okay, that's what we're kind of looking for. All right, so this thing that we're looking for is related to entropy, okay? And we can get an idea for what entropy is by looking at processes that are, oh, sorry, let me back up for a second. It's tempting to think, right, that even in chemical systems, things go towards lower potential energy. And in fact, early on, when people were studying these things, that's what they thought, because most spontaneous reactions are in fact exothermic, all right? And if a reaction is exothermic, then you know it's going from high potential energy to low potential energy, right? It's giving off that energy to the surroundings. So we can get an idea for what really drives reactions, though, by looking at processes which absorb energy, right? So go to higher potential energy, but are nonetheless spontaneous. All right. And a good example of that is ice melting, right? When ice melts, it absorbs energy, right? The water molecules go to higher potential energy, right? But yet it occurs spontaneously above 0 degrees Celsius, right? And notice we see a change in sort of the orderliness of the molecules, all right? And order is can sometimes be thought of as related to entropy, or actually maybe a better way to say that is disorder is related to entropy. And some chemistry books and some people will talk about entropy and disorder as being similar, but it's really not disorder. It's more energy dispersion. And so really a better way to think about that is that the energy of these molecules in the ice structure is very confined, right? It must stay right there, right? But when the ice melts, the molecules can move around, right? And there's essentially, the energy can spread out more easily than it can here, all right? And so really this energy dispersion is really a better way to think about this, although sometimes orderly and disorderly does work, but it doesn't always work, okay? It's better to think about what's happening with the energy. Water spontaneously vaporizing is another example, right, of an endothermic process where the molecules go towards higher potential energy, but yet it's spontaneous at certain temperatures, right? And again, we can see that the energy of the molecules here is more confined, more restricted. When it goes into the gas phase, that energy is more spread out or dispersed, right? So again, this concept of energy dispersion is what drives these processes that go towards higher potential energy. We'll get to the definition of entropy in just a minute. It has a very specific definition, but conceptually, you can think of entropy simply as energy dispersion, all right? If the more energy is dispersed, the higher the entropy. Again, same thing here. This is an endothermic process that's also spontaneous, the dissolving of salt, right? When salt dissolves into water, the energy initially is confined to this lattice, but then when it's dissolved, it can travel all over and energy again spreads out, all right? All right, so here is the definition of entropy, all right? But again, conceptually, it's much easier to think about it as the dispersion of energy, all right? But here's the actual thermodynamic definition. It's a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. See, I told you it was a little complicated, right? But that's okay. If you unpack that, it actually just means energy dispersion, all right? But this is a very precise definition. This is the equation that is used. We won't be using this equation in this class, but I wanted you to see it. S is equal to K ln of W. W is the number of energetically equivalent ways to arrange the components of the system. So when you can arrange the components in many energetically identical ways, that's high entropy. When you can arrange the components in very few energetically equivalent ways, that's low entropy. And let me just give you a quick example, because even though we're not going to be using this equation, I do want you to understand the concept, okay? Think about system A and system B here, all right? This system has two particles, and this energy state right here is an energy state of 2 joules, all right? So each particle has 2 joules of energy for a total energy of 4 joules. There's only one energetically equivalent way to arrange these particles, and that is just as they're arranged here. One particle in this state and the other particle in the same state, right? Each particle with 2 joules, all right? But now let's consider system B. System B, instead of having just one state with 2 joules, has 2 states. One of the states has 1 joule and one of the states has 3 joules, right? All that means that when the particle's here, it has 1 joule. When the particle's here, it has 3 joules. But notice that in this case, I can switch the particles. I can put the red one down here and the blue one up there. All right? So this only has one energetically equivalent way to arrange the particles. This has 2 energetically equivalent ways to arrange the particles. So this has more entropy than this. System B has more entropy than system A. That's the definition of entropy, right? And notice that the energy can spread out. It can spread out over more energetic states, right? That's why entropy is the dispersion of energy. The more places there are for energy to spread out into, the greater the entropy. All right? All right. Now, if we think about the expansion of a gas into a vacuum, that's a good example of a process that happens without any change in energy. Yes, Sophia, bigger spaces, when a particle goes from a small, when particles like a gas go from a smaller space to a bigger space, the same number of particles, that increases entropy. So you're exactly right. You're kind of anticipating here what I'm going to talk about. This gas, if I open that stopcock, right, we know that spontaneously those particles are going to spread out, right? It would be a weird world where, for example, in a room, all the gas particles would concentrate on one side and the other side wouldn't have any gas particles, right? So if you happen to be on the wrong side of the room, you would suffocate, right? That doesn't happen, right? The gas particles spread out over the entire room, right? That's because of entropy, energy dispersion. If all the particles were crammed into one side of the room and the other side was empty, didn't have any gas particles, right? Then all the energy of those particles would also be crammed into that one side of the room, right? But again, energy spreads out. So the energy of those particles is going to spread out over the entire room. Just like the energy of these particles is going to spread out as soon as that stopcock is open, it'll spontaneously flow into there, right? And it'll spread out the energy. Okay? Does that make sense? Rylan, do you have a question?
Yeah, on that previous slide, I was just curious, when we've got the 2 different, 3 joules and 1 joule, would the entropy be greater if the difference between the 2 energies was greater? If we had 5 joules and 1 joule?
No. Not if there's only 2 states. If there's more states and more places for the energy to go, then yes. But if it's just difference in energy, then no.
Interesting. Thank you.
Yeah. And in fact, the entropy might go down because if the 2 particles together can only have 4 joules of energy, then that means that upper state might not be able to be occupied, which means that the particles would be stuck in the same state, which actually happens. Let's see. Sophia is asking if the particles, once they disperse, have lower potential energy. The answer is no. There's no change in potential energy because there's no field here. There's no, the particles don't interact or anything, right? So when they spread out, their potential energy remains exactly the same. The only thing that changes is their entropy. The energy is dispersed, but their total potential energy does not change.
Would that be only if it's from an ideal gas or any gas?
Yeah, correct. It could be true that in some cases, if the gases interact, there could be changes in potential energy. Typically, especially at very, very high concentrations, that can happen, but it's not the it's not the most important factor. Minerva.
Can you go back to the slide with the definition of entropy? Thank you. I just needed to take a picture.
Okay, so here we go. Here's the second law of thermodynamics. For any spontaneous process, the entropy of the universe must increase. That's it. In those words lie the fate of everything that happens. Can you guys hear me? Am I frozen? Oh no. Did I break up?
Yeah, you kind of froze. Maybe
Yeah.
like go
Okay.
back 30 seconds.
All right. Am I back? Can you hear me now?
Yep.
Yeah, I'm not sure why that happened. So this is the second law of thermodynamics. For any spontaneous process, the entropy of the universe must increase. All right. So if a process is to be spontaneous, it has to increase the entropy of the universe. Hugely important. No one's ever seen an exception to this. If you, in your scientific career, discover one exception to this law, no matter how small, you would be rich and famous, you'd win the Nobel Prize, you'd change the planet forever, and you'd change science forever. If you just find an exception to the second law of thermodynamics, that's how much of a giant, that's how many experiments and how many observations back up this law. Not a single exception ever reported, ever been able to be seen. That's because this is the way our universe works. Energy disperses, all right? Now, the nice thing is we can actually calculate this because entropy is quantifiable. We'll see how we can quantify it in a minute, all right? So all we gotta do is take the final entropy of a process and subtract out the initial entropy, and that'll be the change in entropy. And if that change is positive, then the process is spontaneous. And if that change is negative, then the process is not spontaneous. Okay. So heat dispersing, right, is a good example of the second law. All right. Okay. Let's see. Let's start understanding entropy changes by beginning with state changes. How does entropy change when a substance changes its state, like from a solid to a liquid or from a liquid to a gas? So the progress is this way. If you go from a solid to a liquid, entropy goes up. And if you go from a liquid to a gas, entropy goes up. All right. So the entropy of ice is lower than the entropy of liquid water, is lower than the entropy of gaseous water. And again, that's because the energy can spread out, right? It's very confined here in this crystalline structure of ice, less confined in liquid water, and even less so in gaseous water. In addition, as you go through these states, there are actually, not only can energy spread out, but there's more places for that energy to go. So in ice, the only place for energy to go is in the vibration of the molecules relative to one another. But because they're kind of frozen in place, they can't rotate, for example, and they can't translate. They can't move in straight lines, right? So when you go from, let's say, a solid to a gas, now that energy that was constricted can spread out into the rotation of molecules and into the translation of molecules, and then moving in straight lines, right? So there's more places for energy to go. And if there's more places for energy to go, the energy is going to flow into those new places, right? And that's going to increase the entropy. Okay, I'm not going to worry about that. So let me ask you this question and see if this is making sense here. Of the following, which system shows a decrease in entropy? So let me start a poll here and give you a chance to answer that. Okay, make a choice the next few seconds, please. All right, so correct answer was D. So a lot of you got that, but a few of you were distracted by these other things. So let's talk about this for a minute. If you go from a liquid to a gas, entropy increases. So processes, let's write this down. Processes that increase entropy. Liquid to a gas, okay? Because again, the energy is confined in the liquid, it's more spread out in the gas. Solid to dissolve substance, right? If you go from a solid and then you dissolve into the solution, the energy that was confined here gets spread out into the solution. So that increases the entropy too. Solid to aqueous. 2 moles of gas on this side, 2 moles of gas on that side. Let's hang on to that idea. Here is 2 moles of gas, 1 mole of gas, right? So again, when molecules can, when you can make more, when you can take 1 molecule and break it up into 2, that energy that was in that 1 molecule can now spread out more as you increase the number of moles of gas. So any increase, so liquid to solid, solid to aqueous. 3, any increase in moles of gas, right? So when you go from 2 moles of gas to 1 mole of gas, that's a decrease in moles of gas, right? So that decreases entropy. That's the correct answer. Here you go from 2 to 2, right? If you were to go from 2 moles of gas to 4 moles of gas, that would increase entropy, right? Here, it's hard to tell without any more information. You got 2 moles on the left and 2 moles on the right. Okay, so we got liquid to gas, solid to aqueous, any increase in moles of gas. What else? Solid to liquid, right? Increases entropy. Okay. Solid to gas increases entropy. All right. So all these things result in an increase in entropy. Abe.
Yeah, I just had like a question on how like entropy would look like for like electrons. Would it just be considered to have like nearly like infinite entropy just because you can never tell exactly where it is, and since it vibrates, rotates, and moves translationally?
That's a great question. No. Electrons have entropy associated with how they can spread out and how their energy can spread out. And the more their energy that can spread out, the more their entropy. The less it can spread out, the less their entropy. And so, for example, at absolute zero, an array of electrons, right? Let's say in a crystalline lattice or something like that, would be very constrained. Their energy would not be able to spread out very much, and that would have very, very low entropy. As temperature increases, then their entropy would go up.
Oh, okay, okay.
Okay.
And then what would a system look like if it had like would C be an example of where entropy neither increases or decreases?
Right. So it turns out entropy depends on other things in addition to states. So we'd have to look at those other factors. But yes, you're right. We would expect delta S here to be very small.
Okay. That's good. Thank you.
Yeah. All right. Now we want to think about entropy changes in the surroundings, because we know that there are some spontaneous processes in which the entropy actually decreases. So let's think about water below 0 degrees Celsius, right? What spontaneously happens to water below 0? Spontaneously freezes, right? If it spontaneously freezes, its entropy actually decreases. So how is that possible? Well, it's possible because we have to consider the entropy of the entire universe. We can't just focus on the water molecules. There's something else happening here as well, right? What kind of process is freezing, endothermic or exothermic?
Exothermic.
Exothermic, right? Freezing is an exothermic process. So there is heat being given off to the surroundings, right? So when heat is being given off to the surroundings, that actually disperses energy, right? And so when you look at the overall process, delta S universe is equal to delta S system plus delta S surroundings, right? And we know the delta S system for ice freezing, for water freezing, sorry. For water freezing, we know the delta S system is negative, right? Because now we're going from a liquid to a solid, right? And what do we say? From a solid to a liquid, entropy increases. So from a liquid to a solid, entropy decreases. So that's negative. But the surroundings have an increase in entropy. Why? Because the process is exothermic and it gives energy off to the surroundings. Now, here's a very important point because I want all of you to ultimately understand. Why does water freeze? This is delta S universe. Why does water freeze below zero but not above zero? Okay. And the reason is because this delta S universe is temperature dependent. All right. This is temperature dependent, and we'll understand this with an analogy. Okay. Let's say you had $1,000 to give away. You go down to State Street and you find some homeless person and you give them $1,000, right? What's going to be the impact of those $1,000 on that person's net worth? It's going to be large, right? Because they have almost nothing, right? So when you give them $1,000, the change in their net worth is huge, right? But now let's say instead, you walked up to Oprah Winfrey's house in Montecito and walked up to her gate and gave her $1,000. What would that impact be?
Nothing.
Nothing, right? She wouldn't even notice it. It'd be like a rounding error in her checking account, right? So she wouldn't even notice it. So here's the bottom line. When you put energy into the surroundings that are cold, right? So in other words, when you put energy into a system that doesn't have a lot of energy, just like when you give money to a poor person, right? You have a big impact on entropy, okay? You disperse when you put energy into a cold system, you have a big impact on entropy. When you put energy into a system that already has a lot of energy, the impact is much lower, right? So in other words, delta S surroundings is equal to minus delta H system divided by the temperature of the surroundings. So
Wait, does that say delta H system?
that says delta H,
Okay.
right? Because remember what we're saying here. Why does water spontaneously freeze? Because even though delta S system is negative, delta S surroundings is positive. It's positive and temperature dependent. At low temperatures, right? The amount of energy that you give off to the surroundings is enough to create a large change in entropy, right? Just like you're giving money to the poor person, right? Makes a big impact on their net worth. When the surroundings are very, very hot, they have more energy. So putting the same amount of energy into hot surroundings produces less of a change in entropy, right? Just like giving your $1,000 to Oprah, right? Wouldn't have as much of an effect on her net worth, right? So put money in the cold surroundings, big increase in entropy. Put, what I say? Put energy in the cold surroundings, big increase in entropy. Put energy into warm surroundings, smaller increase in entropy, right? Even if it's the same amount of energy. Are you with me? So delta S surroundings equal minus delta H system divided by T surrounding. So let's think about water. We know the delta H system, delta H, the change in enthalpy, right? We know that this process is endothermic. What do you know about the sign of delta H for an endothermic process? See if you can remember.
Positive.
It's positive, right? No, wait a minute. No, endothermic. Energy is going into the system. It's like, oh yeah.
Positive.
Think about delta surroundings.
Sorry, for water freezing, right? We're talking.
No. Sorry, I'm messing this up. Hold on for a second. So, yeah, my bad. Let me start over. Water freezing is exothermic, right?
So it's negative.
Water freezing is endothermic. No, wait a minute. Yeah, water freezing is. Oh, wow. I can't think here. Too much spring
Heat
break.
flows out, right?
Yeah, heat flows out. So it's exothermic, right? Water freezing, water melting, heat flows in, water freezing, heat flows out. Okay, so it's exothermic. Exothermic is negative, right? It's like money going out of your checking account, yeah?
Yes.
So
Yes.
for water freezing, that's exothermic, right? So delta H is negative, right? Okay. So if this is negative, right? A negative and a negative is a positive, right? So delta S surroundings is positive, but it's positive and temperature dependent, right? So here's what happens. At 0 degrees, right? These two are exactly the same. Delta S system and delta S surroundings are exactly the same. So delta S universe is 0. Water and ice coexist at 0 degrees, right? Lower the temperature a little bit, and that delta H has a greater impact on the surroundings, right? Making this bigger and causing the process to be spontaneous. Raise the temperature a little bit, and that energy going in the surroundings has less of an effect and makes the process non-spontaneous, right? So the freezing of water is spontaneous below 0 degrees Celsius, but not above 0 degrees Celsius. So the equation is, yeah, delta S surroundings is equal to minus delta H system divided by the temperature. Okay. Mother's law. All right. Does that make sense? Did I clear that up? Actually, this might help. Here we go. This kind of shows it. At low temperature, here's delta S universe. It's delta S system plus delta S surroundings. At low temperature, delta S surroundings is bigger. Why? Because at low temperature, the energy has more of an impact. Just like giving money to a poor person has more of an impact, right? At high temperature, it would be the other way around. This would get smaller and this would turn negative, right? Because the energy being given off to the surroundings would have less of an impact. Does that make sense? All right, good. Let's see. So this is just summarizing this again. 10 joules in a cold surroundings produces big change in entropy, right? Like giving $100 to a per person. 10 joules into a hot surroundings produces a small change in entropy, right? That's why you have this T down here. Okay, the other thing you can get from this equation is the units of entropy, all right? So this is joules in the numerator and Kelvin in the denominator. So the units of entropy are joules per Kelvin. In other words, one way to think about energy is not, one way to think about entropy is not just energy dispersion, but energy dispersion per unit temperature, right? You have to divide by temperature because it's just like money dispersed per unit net worth or something like that, right? That's where the Kelvin comes in because that's a measure of how much energy is already in the surroundings, right? So the units are joules, energy dispersed per unit temperature. If you disperse the same amount of energy into a cold system, that produces a large change in entropy. If you disperse 10 joules of energy into a hot system, that produces less of a change in entropy. Okay? That's the idea. All right. Good, good, good.
Can I ask
Yeah.
some? Is that
Yeah.
just because heat makes that entropy bigger because molecules are moving faster?
Say that one more time.
Is that just because heat makes that entropy bigger because molecules are moving faster?
Yeah, so if you move, so if you move energy, so if the system gives off energy, right? Then, and you think of energy, and you think of entropy as energy dispersion, right? Then that energy, which was concentrated in the system, is going into the surroundings. So that increases the entropy of the surroundings, yeah? On the other hand, if the system were to absorb energy from the surroundings, what would that do to the entropy of the surroundings? Lower it. Does that make sense? Taylor.
So for the melting of the ice and
Yeah.
the freezing of the ice, the change it has a big effect on right on those kind of border of the states.
Yes.
If like you added 5 joules to like ice that was pretty cold, does it have a big change? Does it like, how do I say this? Does it have a big change on the entropy still, or even though it doesn't really change the state?
Yes, it can. Well, if you add 5 joules of energy to ice, let's say that it was at 100 Kelvin, that would have a greater impact on the entropy of the ice than if you added 5 joules of heat to ice that was at 200 Kelvin.
Okay.
The colder the temperature, the more the impact of those 5 joules. Just like the poorer the person, the more the impact of those $1,000.
Okay. Okay. So that's when that makes sense now. Okay.
Okay, so let's look at this example here. Let's say we have this reaction. We know that delta H is minus 255, right? So the first question was to find delta S surroundings. So that's easy. Delta S surroundings. We just have the equation for that. Minus delta H system over temperature, right? So delta H system here is telling us it's minus 255 kilojoules, but it's minus that number, right? So minus 255 kilojoules, which makes it positive, divided by the temperature, and the temperature is 298 Kelvin.
Wait, does it not need to be in joules? It can be in kilojoules?
It could be in kilojoules, but usually we do report it in joules. Okay, so that
Okay.
would be positive 255 times 10 to the third joules divided by 298 Kelvin. And if you work that out, that comes out to be positive 856 joules per Kelvin. Right, so delta S surroundings is always just delta H system divided by the temperature. Yeah, you with me? Part B, find the sign of delta S system. Okay, what can you tell me there? 3 moles of gas on the left, 1 moles of gas on the right. What can you tell me about the sign of delta S system? Positive or negative?
Negative.
Negative.
Negative. Negative, right? So C, is the reaction spontaneous? Well, delta S universe is equal to delta S system plus delta S surroundings. Well, we know that this is negative. We don't know the value of that. And we know that this is positive. So we really can't tell delta S universe, right? Unless we get a value for delta S system, right? We'd have to figure out what the value is of delta S system in order to calculate this, all right? Does that make sense? Okay. Here's one for you to try. Very similar to the one we just did. Give it a shot. So let me back up for a moment to the previous question. I'll come back to this one. I'm gonna leave the poll open for a second. This is the one we did before, right? We found delta S surroundings, right? Since delta H was negative, we knew that delta S surroundings was going to be positive, right? We knew that 3 moles of gas goes to 1 mole of gas, so we knew the delta S system was going to be negative. So the system and the surroundings had different signs, right? This was negative, this was positive. So we really couldn't tell, right? And it would likely depend on temperature, right? Because depending on if this could be made bigger by going to colder temperature, maybe that would be enough to overcome this, right? But this one, without more information, you can't tell. This one, you can tell. Okay, you can tell. And why is that? Because first of all, if we do the same thing, if we think about delta S surroundings, right? We know that's negative delta H system, right? Divided by T. Well, delta H system is negative, so that's negative a negative divided by T. That's going to equal to some positive number, right? And then B, what do we know about delta S system here? We have 1 mole of gas here and 2 moles of gas on the right. So what's delta S system? Positive or negative?
Positive.
Positive, right? So delta S surroundings is positive, delta S system is positive, delta S universe is equal to a positive number plus a positive number, right? So what do you know about delta S universe?
It's positive.
It's positive, right? And if it's positive, then it's spontaneous, right? So the right answer is A, right? And we did okay. Some of you said it would depend on temperature. In this case, it would depend on temperature because these have different signs. But in this case, it doesn't depend on temperature. It's spontaneous at all temperatures. Okay, good. All right. Any questions?
If delta H had been positive in the last case, would we have been in a scenario where it would have depended on temperature?
If delta H would have been positive?
Yeah.
Yes,
Okay.
correct. Correct. So when the signs of the system and surroundings, when the signs are opposite, that's when it depends on temperature. If the signs are the same, so for example, what if we had a situation where this was positive? So let me give you one more situation and see if this makes sense. Let's say we had A gas plus B gas going to AB gas. So this is gas, that's gas, all right? And we have delta H equals some positive number. What can you tell me about the spontaneity of that? Spontaneous or non-spontaneous? Let's just think about each component, right? Delta H system, what can you tell me about delta H system? Positive or negative?
Negative.
Negative. Good. Delta H surroundings, positive or negative?
Negative.
Negative. Delta S universe, positive or negative?
Negative, so it's non-spontaneous.
Right. So non-spontaneous. Does that make sense? Delta S system right now, we're just finding delta S system based on the number of moles of gas. So since you go from 1 mole of gas to 2 moles of gas, we know the delta S system is positive, right? Because we said earlier that any increase in number of moles of gas is an increase in entropy, right? So that's how we're determining delta S system. Minerva.
I wanted to ask if you could answer that question, the one that you have on the paper, by counting the number of moles, or would you have to follow the same process?
Delta S system you can find by counting the number of moles of gas. So any increase in the number of moles of gas tells you the delta S system is positive.
I mean, for like determining if it's spontaneous or not.
So determine if it's spontaneous, you have to look at both delta S surroundings. Oh shoot, this was supposed to be delta S system. You have to look at both delta, and this was supposed to be delta S system too. I mean, sorry, delta S surroundings. Sorry, ask me a question again, Minerva.
So I was asking if you can determine spontaneity, or if it's spontaneous or not, by counting the number of moles from the reaction.
Okay, so the answer is not just from doing that, but that's one of the steps, okay? Because ultimately, spontaneity will be determined by delta S universe, right? Which is equal to delta S system plus delta S surroundings, right? Delta S system you can figure out by counting the number of moles of gas, right?
Okay.
So this one, what's delta S system for this reaction, negative or positive?
Isn't it positive, right?
What, 3 moles of gas, 1 mole of gas?
So positive, because you're left with 2.
No, if you decrease the number of moles of gas, that decreases entropy. Increasing the number of moles of gas increases entropy.
Oh, okay, so it's negative in this case.
Correct. Exactly right. What about this one? What's delta S system for this one?
Positive.
Correct.
Positive.
Correct. Yep. Does that make sense?
Yeah.
Perfect.
Okay, thank you.
Yeah. Abe.
Oh no, I was just confused on the delta H is that's pretty much
Sorry.
it.
Yeah, I meant those are supposed to be delta S's.
Wait, but now that I'm looking at it, when we're looking at the delta surrounding, why was that one negative? Just to be clear.
On this one,
Yeah,
because delta H was positive.
you're right. Yep, I get it now.
Got
Yep.
it?
Mhm. Yep.
Okay. Good. So let's just look at this one more time just to make sure we have it right. This one that's up on the one that's up here right now. What can we say about delta S system for this one?
Positive.
Positive, right? What can we say for delta S surroundings for this one,
Positive.
Positive.
right? So what can we say about delta S universe for this one?
Positive as well.
Positive as well. Or spontaneous. With me? Phew, I don't know why that was so difficult for me to explain. I'm so sorry. It's the signs can be a little bit confusing, right? But if you think about it with each component, what's delta S system, what's delta S surroundings, and then what's delta S universe, which is the sum of them, then that should help. Okay. All right. So let's see. I think I'll just introduce this point here of Gibbs free energy, and then we'll call it a day because it's a Monday. So we already saw that delta S universe is equal to delta S system plus delta S surroundings. What we would really like is a more convenient way to determine if things are spontaneous. And by this, I mean, is there a way in which we can only focus on the system? And the answer to that is yes. We can come up with this thing called free energy, which is called G. Okay, and its definition we can get like this. So first of all, delta G is equal to delta H minus T delta S. And this is all for the system only. We don't even have to think about the surroundings.
Can you scoot your paper down?
Yeah.
Thank you.
Just notice that. This is for the system only. We don't have to think about the surroundings. This change in free energy is equal to delta H for the system minus T delta S for the system. And it turns out the delta G is equal to minus T delta S universe. And if you want to see the derivation of that, you can look in the book. We don't really need to do it right here. But the point is that with this thing called free energy, which we define the change in free energy as delta H system, okay, this is all system, minus T delta S system, all right, system only. Then if we calculate this quantity, it's proportional to minus T delta S universe. So in other words, a negative delta G tells us that the process is spontaneous, and a positive delta G tells us that the process is non-spontaneous. So notice that delta G is equal to minus T delta S universe. So in other words, delta G and delta S universe have opposite signs, okay? That's the main thing, all right? So if you calculate delta G and it's negative, that means that delta S universe is positive and it's therefore spontaneous. If you calculate delta G and it's positive, then that means delta S universe is negative and that's non-spontaneous, all right? So we're gonna focus a lot of our effort in this chapter because at the end of the day, we wanna understand what reactions are spontaneous and which reactions are not. we're going to focus a lot of our efforts on this delta G. All right. And so we'll talk a little bit more about that next time. Okay. But I think I'll end there. A lot of concepts here. Some of them are a little fuzzy, but with a little bit of time, I know that they'll sink in and they'll make sense. Okay. Any questions before we sign off?
Why free energy?
Why is it called free energy? It's actually, the definition of it is, it's the energy that's free to do work in a chemical reaction. That's the definition of it, but that's not very helpful when it comes to understanding how it relates to spontaneity. All right. So that's why I'm not going to really worry about the definition for right now, except for to define the change in free energy. And so the way you want to think about this is basically, if you find the change in free energy, you can determine, if you find the change in free energy for a reaction, you can determine if it's spontaneous or not. Okay. How do you do that? Figure out delta H for the reaction, figure out delta S for the reaction, and plug it into this formula. All right. And that is inversely proportional to delta S universe. Right. So that makes it very easy. Right. All you got to do is, if you have a reaction, okay, what's delta H for the system? What's delta S for the system? Plug it in, figure out the sign of delta G. If it's negative, it's spontaneous. Any other questions?
So just to be clear, and somebody just asked this in the chat right now, there is no post-lecture assignment?
Correct. There's no
Okay.
post-lecture assignment today.
Sweet.
Yep. Ease you back into this. Anything else? Taylor.
Okay, this is kind of a question from a while ago.
Yeah.
I found in the chat. Can the entropy be dependent on the type of compound or element, not just its state or temperature?
Correct. And we are going there. We'll look into that question a little later in this chapter. But yes, absolutely. It's not just its state, it's the type of compound for sure. So we start out with the more general things like the states, and then we'll dive deeper into figuring out the entropy based on the compound itself. You're absolutely correct.
Okay, cool. All right, thank you.
Yep. Okay, I think I'll end class officially, but I will stay on to answer any of your questions. If you don't have any more questions, you are free to go. Thank you so much. Happy Monday. See you all on Wednesday. Goodbye.
Thank you. Happy Monday.
Thank you.